Welcome back to the course. Today we have sixth lecture for the course Corrosion Failures and Analysis. And today is sixth lecture. And topic we will start discussing on galvanic corrosion. Now, if you see the uniform corrosion mode, and there you could find that cathodic and anodic reactions are taking place, and cathodic and anodic reactions are actually uniformly taking place over the entire metal surface. In fact, at the end of while we started looking at different aspects, the mechanisms of uniform corrosions, we talked about rain droplet corrosion. In fact, while talking about rain droplet corrosion, we mentioned that it is basically in a galvanic mode where cathodes and anodes are forming at specific locations. It is not happening at over the entire surface covered by the droplet. Okay. So, it is basically, if you go back and see, this is the droplet, and we could see that the corrosion pattern is like this. So, in the center part we have the highest corrosion, and the center part is preferentially anode, and the periphery region is preferentially cathode. And this happens because of the change in concentration of oxygen or the dissolved oxygen in the droplet around that periphery. Around the periphery there is no change in the oxygen concentration, but in the center part of that particular droplet we do experience oxygen depletion, and that is what there is a change in concentration of oxygen, and it leads to a concentration cell, and that concentration cell leads to this difference in corrosion behavior across this area, across this area. So, and we said that this is basically a corrosion cell, and that corrosion cell is leading to difference in corrosion. There are two segments, and that cell actually leading to that particular typical formation of those cathodes and anodes. The center part is corroding more, and it is a localized effect is coming up. And we related this particular phenomena with the uniform corrosion, saying that the droplet is also forming sometime here, sometime here, sometime here. So, finally, those localized corrosions are actually connected together and then having a uniform mode. Okay. So, this segment is basically uniformly corroding, but if you look at one particular droplet, it is basically localized. The center part is having more corrosion rather than the periphery part, and this is a serious galvanic effect. Now, question is whether uniform corrosion, though as per the form we say that this is uniform corrosion, but if you carefully look at the mechanism is nothing but the galvanic corrosion. Why? Why do you say that mechanism is galvanic corrosion? Because corrosion is nothing but a galvanic cell formation. This is one, and the second part is metal dissolution is the anodic process, and this is nothing but the corrosion. But as we know, the corrosion has four parts: anodes, cathode or anode, let us say anode, cathode, conductor and electrolyte. Fine. So, these 4 parts, out of that this talks about this particular phenomena, but otherwise all the parts are required, otherwise corrosion may not take place. Fine. Now, coming to this galvanic cell formation, let us see whether uniform corrosion is also a galvanic mode. Let us talk about iron corrosion, what we have already explained. So, iron plate in air where moisture is present. So, the cathodic reaction is nothing but H2O plus 4E O2 plus 2H2O equal to 4OH minus. This is the cathodic reaction. And then anodic reaction, which is corrosion, is plus 2. And these two reactions must happen together, otherwise singularly this reaction cannot take place. And if we see that why this reaction continues, because if we consider their standard reduction potential for those two reactions, for the first reaction the standard reduction potential is volt, and the second reaction E0 equal to minus 0.44 volt. So, these are with reference to hydrogen, the standard hydrogen electrode. Okay. Now, why do we have these reactions to continue? Because if we try to find out free energy change, which is delta G0 is equal to minus NF E0, which is the E0 is the standard reduction potential for the cell, and for this complete cell the standard reduction potential E0 would be find out, and let us say if it is E1, if it is E2, E1 0 minus E2 0, which becomes, if they are in standard state. So, which is impossible, but let us assume that this is the value what we have. In actual cases these values would be different, remember, because the iron ion concentration may not be 1 and these concentration may not be also 1. So, that case the things will be, these values would be different, and that will be calculated on the basis of Nernst equation. And what is the what are the Nernst equation? For the reaction 1, Nernst equation would be E equal to E naught plus RT, and here the electron is 4F ln, and we know that oxidant concentration divided by reductant concentration. Here and oxidant part is in this case here, this is oxidant and this is a reductant. And here in this case this is oxidant and this is reductant. And how to recall? Whenever you have some difficulty in understanding which one is oxidant and which one is reductant, write everything in reduction mode. For example, Mn plus Ne equal to M. So, that time this would be oxidant and this would be reductant. Or you just go to hydrogen reaction, and we know hydrogen is a very good reducing agent. Hydrogen is a very good reducing agent. So, this has to be reductant and this one has to be oxidant. Fine. So, now since we write this way, so we can write this is 0.401 for the first reaction plus RT 4F, F is Faraday. Here what are the terms? F is 1 Faraday, which is 96500 Coulomb per mole of electron, but this value is little different 96486 488 something like that. So, we write it, we round it off to and write it 496500, and R you can take it as universal gas constant 8.314 joule per Kelvin per mole, okay, and temperature is in Kelvin. Okay. So, now you can write partial pressure of oxygen, because this is the oxidant, into hydrogen water concentration and OH minus ion 4 to the power 4, and second case this is E1, this is E1, this is E2, E2 naught plus RT, here the number of electrons involved is 2, ln oxidant, here it is iron ion, and this is the equation, Nernst equation. So, now depending on the concentration here of that iron plus plus, or depending on oxygen presence, partial pressure of oxygen and OH ion concentration in the solution or the electrolyte, we can have different E1 value. So, that time instead of E1 we have to write E1 minus E1 naught, you have to write E1 minus E2, fine. So, now once you do that, you will see that that value would come 0.841 volt. And now, if I apply this particular equation, we see that delta G naught is nothing but minus. So, now in this case it will be this value, but if you take E1 and E2 this value, then you have to take consideration of this particular number. So, that value would be different. Okay. Now, NF E naught. So, N would be decided by equilibrated condition. Okay. So, now this E naught is positive, hence this would be negative, and we know if the free energy change is negative, we do get the reaction to continue. Okay. That means the free energy change, and if you take non-standard condition, that time this would be delta G would be minus NF E. So, that time no standard values are to be taken, we have to calculate the actual value, fine. So, if this time also this will become positive, negative. So, that is what both this reaction will continue if we have supply of oxygen as well as there is a huge source of iron, because the iron plate is corroding. So, now this particular effect is nothing but the galvanic effect. So, this is coming from galvanic effect, and this is a typical electrochemical galvanic effect. So, that means here the iron corrosion is actually a galvanic corrosion, but interestingly the form is uniform, because this galvanic corrosion is taking place over the entire iron surface. So, that means this is the iron surface. So, everywhere we are getting both these reactions, and there is no specific localized cathodic or anodic reactions. So, it is basically just like, for example, in this case droplet case, we see that the peripheral part is preferentially cathode, the central part is preferentially anode, but there is no such preference. Hence, the corrosion is taking place uniformly over the entire cross section. So, that is what we call it uniform corrosion. So, galvanic uniform corrosion from the fundamental mechanism point of view is actually galvanic corrosion if we consider the electrochemical reaction part, but since it is happening over the entire surface without having any localized positioning of cathodes or anodes, that is what we call it uniform corrosion. But theoretically, if we consider reaction wise, it is galvanic effect. But if we come to galvanic corrosion part only, we would see that the galvanic effect comes specifically what we call it as a galvanic effect, that when we have preferential locations of cathodes and anodes. preferential locations of cathodes and anodes. Okay. So, this is extremely important aspects. Now, whenever we talk about preferential locations of cathodes and anodes, it can happen on the same plate due to concentration effect, that is what we have understood in the rain droplet example, or it could happen some metal deposition, and that metal deposition can happen because, for example, if we talk about one example I have cited, that is the copper deposit on the steel plate, and that copper deposit can lead to a galvanic effect. Okay. So, that is also there. So, those part we will talk about later, that how come this preferential location effect would come, and preferential locations of cathodes and anodes. But let us understand from the definition point of view, usual textbook what is written. They say that galvanic effect comes when two metals or alloys of different electrochemical nature or activity leads to galvanic corrosion. Here they only talk about metals and alloys, fine, but we will see that it is not only specific to metals and alloys, there are effects due to concentration also, fine. So, there the same galvanic effect can appear on a same plate without having different metals. Now, but this is a very, very common definition you will find in many books, I mean almost all the books on corrosion, fine. Now, first understand this and then we will get to this part, okay, preferential locations of cathodes and anodes. And in fact, these preferential locations can come, okay, if we, since we have talked, let us understand that what are the situations preferential locations comes. If we take note of that, one is of course usual definition, two different metals, alloys there, and interestingly one part I missed is electrically connected. For example, if one metal is here, another metal is here, and they are in electrolyte, until and unless they are in electrically connected, you hardly experience, you do not experience galvanic effect, okay, which actually relates to preferential locations of cathodes and anodes. Okay. This galvanic effect would come when they are electrically connected, fine. So, this is one. Second part is what we have understood, if we see droplet is basically coming on a same plate concentration difference of participating electrochemical species, electrochemical or chemical species. It can be either let us say oxygen, copper ion, etc., they can lead to galvanic effect. So, that would lead to preferential location of cathodes and anodes. Okay. So, this is extremely important, fine. Now, there could be possibility of on a plate, same plate, and whenever I am talking about same plate, the metal plate. There could be possibility of deposition noble or less active metal. there could be possibility of on a same plate there could be, or in this case metal, rather instead of metal I would say alloy plate, and here all the cases you can put alloy, and here also alloy, but here I am putting only alloy. Okay. So, there could be local difference in concentration of a particular element. Fine. For example, this one we have already seen, the droplet experiment, droplet example. This one we will explain again, that is copper deposit on iron plate. And this one we have touched it upon, but we will discuss more when we talk about intergranular corrosion. We will see that the chromium depletion leads to strong galvanic effect across grain boundary. There could be effect due to crevice, or rather on a same alloy or metal structure. You can have crevice or pitting, that could also lead to a strong galvanic effect. We will see later. For example, if this is the crevice, you will see that this crevice part, or if it is a pitting, let us say this small pit has formed, the pit part, this will be preferentially anode, and this, and here also this crevice part would be preferentially anode, and around that section will be preferentially cathode. And here also around this crevice part you will see these are cathode. So, again there is a situation of preferential anodes and cathodes. So, again coming back to this particular statement, this is extremely important while understanding galvanic corrosion. Fine. So, that means these are the normally observed practice, observed situation, we could get preferential anode. And for example, one such example, let me just show you. For example, on a same alloy or metal plate structure, there could be difference in strain or stress field, and that could also lead to preferential positioning of anodes and cathodes. And this one such example we will talk is about cavitation damage, or in case of stainless steel we will also see that if the strain relief operation is not done properly. So, that is not particularly related to this, but at least on a same structure sometimes at one location you could find that that is strained heavily, and another location it could, you could find that that is not strained heavily. I will also show one such example. I have that particular rod. If you, and also you can also go back and check on the roads. On the roads you will find that reinforced bars are actually made into a kind of this kind of shape, okay, a square shape. Or sometimes you would find in the household application some object is bent, and whenever there is a bent, this bent location these are extremely strained. So, that location has the preferential anodic tendency. So, this is preferential anodic tendency, fine. So, then also you can get galvanic effect on those corners part. So, this particular one thing I will show it in the next lecture, next class. Okay. You will see that there I have a rod I have collected from the roadside, and you will see that on the bent portion the corrosion is concentrated, and that actually happens because of that strain effect. Okay. So, these are a common practice. We will discuss more on this as we go ahead, but at least you should appreciate that whenever we talk about galvanic corrosion, from the definition wise, it is not only two metal or two different metals or alloys which are electrically connected exposed to an electrolyte, but at the same time you can have that galvanic effect because of other reasons without having two metal contacts, okay, two different metal contacts. So, let me conclude here that galvanic effect is actually due to preferential location of cathodes and anodes, not only two metal contacts. So, that is what I would like to stress upon here. So, we will continue our discussion in our next lecture. Thank you.